All right. Welcome to lecture 8 for the mathematics of data model, CS 2810. Um, this is a course in Northeastern University, and I'm Professor Wu. So now, previously we talked about the concept of span, now row space, column space. It's really, really important that you have mastered those concepts before you move on. If you don't, well, a lot of these new things are not going to make sense. So I recommend you watch lecture 7 a couple times and really, really like try all the practice questions before you move on. So, because going forward, we're going to be using these ideas to build on top of other things. So, anyways, let's get started. Last time we were talking about the concept of null space, the null space, right? So given a set of bases, if you remember, a basis is basically a bunch of vectors. And by using these bases, it essentially spans a space, right? So given these set of bases, and we're going to let these vectors be the columns of the matrix A, okay? A null space is a set of all possible solutions for X, right? X, such that A times X is equal to 0. So remember, A was a set of vectors, which we were calling them bases. And X is a vector here, which in the end you will multiply down, like X multiplies down the vectors. Now, remember, the definition of null space is that it's the space, the set of all possible x's. So the set of all possible vectors, such that when you multiply by A, it gives you a 0. and and that's important because you can view this as some kind of system, right? These set of basis functions as a system, and that it is possible or not for you to zero it out without resorting to just setting everything to 0. Because obviously, if you just set x1, x2, x everything to 0, you're going to get a 0, and that is going to be like a pretty trivial case. But there will be cases that you don't have to set them to 0, and you will be still able to zero them out. Anyways, so to find the null space, the way you would do it is essentially create an augmented matrix with 0 as the solution, right? So here's the matrix, and you want to see what is the x that will give you 0. So you just put the 0 as the target. And then once you've done that, you essentially solve it for the reduced row echelon form, the REF. Okay. So first, you take this, like if A is this, you will put it in the augmented matrix where 0 is the label. Next, we turn it into reduced row echelon form, right? And from the reduced row echelon form, we can see that that's just the equation, implying that x1, x2 are both zeros. And like I said, when the solution of the null space is a unique solution at 0, that's called a trivial solution, because like 0 times anything is obviously 0, right? So that's the trivial solution. Now, let me give you another example here where we don't have a trivial solution, right? Once you reduce the augmented matrix down to REF, sometimes you might end up with something like this, right? If this is the REF, now you write it in the solution case, notice that this has infinite solutions, implying that the solution will look something like this. Now, this is actually a space. If you remember from the last lecture, we talked about how a vector can define a space, and it defines it by multiplying by some constant. And over here, you're essentially saying that the null space is any number multiplied by this vector, right? So that creates a space right here. And hence, this is actually a space that happens to be the null space. And notice that the solution is not trivial, okay? Okay, last time we also learned about the concept of span, right? So here's the vector, 1, 1, the span is essentially this entire thing, entire line. Basically, anything that multiplying by some constant alpha it could reach. And the definition of span of a vector is the set such that if you pick any real number, plug it in here, and it will become an element of this set. That's just with one vector. But if you have multiple vectors with a span, it's essentially the linear combination of them. So you have v1, v2, v3, and you can essentially pick any number, any a, b, c, d, whatever, in here, and that will be part of the set. So from this, you can see that if you have two vectors, 1, 2, so any combination of them will be part of the set. So the set will essentially be this 2D plane. Anywhere this 2D plane touches, it implies that these two vectors can also reach. Okay, now if you have two vectors, it could, like you see 1, 2, now you can see how it's spanning 2D, but it doesn't always span 2D. But if you have two vectors, it at most spans 2D. Okay, remember, I think during class I was saying how if you have a vector that's 10 dimensions, right? So on and so forth, so on and so forth. 10 dimensions. You have two vectors. The span of these two vectors is still 2D. Okay, it's not spanning more, just because each vector has more dimensions. Okay. Now, these vectors that's used to create these directions, such that to create the space, right? These vectors that create the space, they're called bases. So having certain bases, having the right bases allows you to span a certain space. Now, just because you have two vectors, it doesn't mean it's going to always span 2D, right? Because they could be the same vector. You see 1, 1 and 1, 2. They're exactly the same vector. So you're not adding additional dimension to this. And the true dimension spanned by the set of vectors is called a rank. Okay? So rank is really important because that tells you out of maybe 100 vectors, it only spans maybe 3 dimension, and this will be the rank. Now, this leads us to two possible cases. The first is when the rank is the same as the number of bases. Okay, so if the rank is the same as the number of bases, it means that, like, if you have two vectors, right? You have two bases here, and the rank is 2 because the dimension is 2. This implies that every vector is contributing to a new dimension. And let's say we have 3 dimensions, right? Now every vector is contributing to the 3 dimension because you have 3 vectors and the rank is 3, which the span is 3 dimensions. But in other cases, so the first case is when the rank is the same as the number of bases. But the other one's rank is fewer than the number of bases. This means that you have lots of redundant vectors. So let's say you have 3 vectors again, 1, 2, and the third one is right here, 3. So the third one, 3, 1, 2, 3. So the third one is actually on the same plane as 1 and 2. 1 and 2. So imagine 1 and 2 is the x and y axis, and 3 is also on the x and y axis. This means that 3 is on the same plane, and you are not adding additional dimensions, therefore. Okay? So the key here is redundancy. Like, maybe I can draw this a little bit better. Let me see. If you have, here's the x-axis, here's y-axis, here's the z-axis, and therefore, let's say the first vector is like this, second vector is this, and the third vector is like this. Okay, so you can see they're all on the same xy plane, and therefore the third vector is just a redundant vector because you're still at most spanning 2 dimensions. Okay. Now, these two cases have names. When the rank is the same as the number of bases, this means that the bases are every basis is expanding the span larger, right? And these are called linear independent. Okay? These vectors are linearly independent. Now, when the rank is fewer, right, than the number of bases, it means there's redundancy in the vector, and that these are called linearly dependent. So the vectors are dependent of each other as opposed to independent of each other. I don't think that picture helped. So yeah. So this is what you need to remember. When is it independent and when is it dependent? Okay. Dependent is when the rank is fewer and that you have redundancy. And independent means that the rank is the same and that every vector is expanding larger. So this is interesting because if you have like x, so vector 1, vector 2. So these two are independent because you have two vectors and it spans two dimensions and the rank is 2, right? But if you have this and this, right, then they're dependent. So dependent in a way is kind of, yeah, it's difficult to grasp this idea conceptually. Yeah, it's I think the best way to think of it is through the concept of this redundancy. If when there's redundancy among the vectors, I think I just drew this actually. This is when it's independent, and this is when it's dependent. Okay. Now we can have a formal definition of linear dependence. It's saying that a set of vectors is linearly independent if and only if. If you remember what I meant by if and only if, it means it implies the logic in both directions. So if this is 0, okay, if the equation, so imagine these v's are vectors, okay, it's saying that you can obtain this with some kind of constant c1, c2, ck, all the way to ck, has only trivial solution, okay, then it's independent. So let me go back to the idea of null space. We kind of talked about that. So it's saying that the null space, right? If the null space only has trivial solution, then it's linearly independent. This you intuitive. Let's see if I can help you gain an intuition of why this definition works. It's because if if there is uh, if there's redundancy, let's think of it in terms of redundant. There's some vectors that's like, let's say this one is redundant. If it's redundant, it means that these other vectors span this vector here. Okay, so it is possible to span it. If you can span it, it also spans the negative. Therefore, you are able to turn this into 0 without setting C1, C2, C3 all of them to be 0. Okay. Similarly, if this one is spanned by them, you can also subtract this out. Therefore, if any one of them is spanned by the rest of them, then that's dependent. Okay. If it's not spanned, then the only possible solution, this is possible, is if you set every one of these to be 0. Okay. So you might want to listen to that logic a couple times, like rewind the video, and because yeah, this is not a simple thing. You got to really think about it. So you can see this is essentially the same as finding the null space. And if the null space only has a trivial solution, then it's linearly independent. This is why I emphasize make sure you understand the concept of null space, right? And there are multiple kind of null space, the trivial and the non-trivial solution. Okay, but in summary, what I'm saying is linear dependent, if there's no space, right, is the trivial solution. Linearly independent is if there's no space solution is a non-trivial solution. So this you will have to remember. This is definitely This is definitely going to be on the exam. Very, very important. Okay, so let's do a quick practice together to identify if they're dependent or independent. So let's say we have these set of two vectors, right? Now the set of two vectors, you can like put them into augmented matrix and convert them into REF. So once you have them in REF, notice that they are only trivial solutions. So I don't know if you remember 1, 0, 0, 1, 0, 0, and this is x1, x2, therefore equals to 0, 0, 0. Therefore, it's saying that x1 is equal to 0, x2 is equal to 0, and 0 equals 0. That's what that's saying, right? And therefore, if they're only trivial solutions, again, that means they're independent. Over here, the REF, you can see that it has a space in there. So this becomes x1 plus x2 equals to 0. Therefore, x1 is equal to x2, and x1 is equal to minus x2, and x2 is equal to x2, which is minus 1, 1, x2. Okay, so this one like has a non-trivial solution. Therefore, if it's non-trivial, then they are if they are non-trivial, then they're independent. There we go. Even did I write independent both times? Oh, great. I need to go back and change this. All right. Let me make sure this one is correct. So if their null space is the trivial solution, then they're independent. So this one is dependent. Sorry. This one is dependent. Okay. I need to make sure I go back and change that. Okay, let's look at the third one. Over here, you can see that the null space has a non-trivial solution. Therefore, they're dependent. Over here, the null space has only trivial solution. Therefore, they're independent. So you got to go back and really make sure you understand like the concept of null space and then dependency. So here's another one. Like, are these linearly independent, right? Why don't you pause the video and give it a try? Okay, make sure you pause the video so I can move on with the video. Okay. So in this case, notice once you reach the reduced row echelon form, you basically have the really nice unique solution, and this unique solution means that it's independent. Okay. Also, by the way, rank. I think I previously mentioned that rank is the true dimension. Is the if you have multiple vectors, what is the actual dimension that the vectors span? That is called rank. Now, you can identify the true dimension by looking at the reduced row echelon form. When you have the reduced row echelon form, you simply have to count the number of leading variables, also known as the pivot variables, and it'll be 1, 2, 3. Therefore, here the rank will be 3. Okay. Once again, pause the video, see if you can give this a try, right? And see if you can identify if they are linearly dependent or independent. Okay, pause the video because I'm moving on. So in this case here, once I've reached the reduced row echelon form, over here you notice you have 1, 2, 3. So these are all leading variables. So that means the rank is equal to 3, right? Leading pivot variables. And because you have one free variable, that means it's not like a non-trivial solution. So actually, maybe the easier way is just reduce to the reduced row echelon form, and if there's any free variable, then it's going to be dependent. That's actually not a bad rule. Anyways, let's move on. So why do we care about linear independence, right? Well, linear independence is really important in the concept of data representation and compression. Like, how do you compress data? So let's say you have a bunch of vectors, right? So one way to represent these vectors is to simply make them as columns of a matrix. So that's one way you can do that. You can write this in a file and save them. But you can imagine this is only 5 vectors, but you can have 5 million vectors. So this could take up a lot of space in memory. Another way is to identify useful bases as an underlying assumption. So instead of representing this whole data this way, we could actually represent very very small, like compress it into very small amount of numbers, and then still be able to retain all the information. Now, how is that possible? So imagine if we let the first column be the basis, right? The vector we want to use. Well, once we have this basis, then what it is, we're going to call the basis V. So if you take 1 times V1, which is it's just itself. Now notice if you have 2 times V2, 4 times V1, 6 times V1, and then 1 times V1. So what's happening is, notice 1, 2, 4, 6, 1. 1, 2, 4, 6, 1. So as long as you know this is going to be the column vector as the basis, you don't need to store this whole thing. All you need is to store these numbers. Okay, so the concept of basis really allows you to compress data with some kind of assumption. So if you use the assumption where the first column as the basis, then suddenly, like we don't need, like, look how many numbers is 1, 2, 3, 4, 5. So there's 20 numbers versus 1, 2, 3, 4, 5. 5 numbers. So using the first column really compressed it. But another way is we can use the first row as basis. So this is going to be the row. And notice this is, if you use that as the basis, then it's 1, 2, 1, 0, right? You take this, multiply by 2, it'll give you this. Multiply by 1, multiply by 0, it will give you this. So we can just write 1, 2, 1, 0, right? This is even smaller than this. And if we had used the first row as the basis, this will essentially allow us to compress the data as much as possible. It really compress it. Okay? So by intelligently identify these like set of bases, we can drastically compress the same data, and like we can represent the same data with very little amount of numbers. Okay, so this like dependence, compression, they're all really related. So let's pretend you're Google, right? How would you be able to index the entire internet? I mean, the entire internet is gigantic, right? It would be impossible to store every page in the world and search through each page at a time. But imagine you can find a minimal set of key bases. Remember, we just use a basis to really compress the data into some kind of representation. And then, as long as these bases can span the entire internet, so you don't need every single page of the internet, right? You can represent them with very few numbers, comparatively few numbers. And then each page can be represented as a vector. So you can kind of picture it that way. Now, if you convert your search word, so whatever you're searching, and you also convert that into this vector, right? Similar vector, you have a way to do that. Then, like you can, basically you can say, okay, if this is your search term and these are the web pages that's close to you, you can essentially cut it off and say, these are the ones I want to show to my user, right? So like the nearest 30 pages to you. Now, this is not exactly how Google did it, but you kind of get the point of how compression could be really useful. Right. In Google, I do think they use a set of bases called the principal eigenvectors, but I never really read their algorithm. It's actually publicly available, but one day maybe I'll read it. But I do know, based on what I heard, I think they do use some kind of principal eigenvector idea somewhere in there. Anyways, again, compression of data is literally how our modern life is possible. Like Zoom, if you want to use Zoom, there's no way you can send the raw data. You essentially have to compress it really, really small to send it through the internet, or else your internet would just be jammed up all the time. Like if you want to watch video, how do you think we get the high def streaming? Like, yes, we do get larger bandwidth, but we simultaneously were making the videos smaller so we can send a little bit, right? Basically, everything coming in and out of your phone, your tablet, right? They're all compressed. Like, if you don't compress it, you're essentially just sending a lot of information. And for example, MP3s, right? If you have some data, you can compress it multiple ways. But if you compress an MP3, look at the difference. This is 86 megabyte, and then this is 5 megabyte. So when you're sending files across the internet, you don't want to send this, right? You can essentially achieve the same information sending something much smaller, and that speeds up the whole process. Now, compression is really important, and therefore, like these ideas of bases, independence, nonlinear independence, they're all the underlying math that you would need to understand in order to know what like any of these compression is about. So if I were to put all the concepts together in data science and machine learning, you will see various ways to represent the data, right? You can represent the data as matrix, which is very common. You can also represent the data as independent bases, right? Like that's another way to do it. We can identify if a set of vectors are linearly independent or dependent, depending on whether their null space is trivial or non-trivial. So that's the linear dependence and independence is all about identifying the null space solution. Now, the actual space spanned by these vectors are called the rank. Uh, if you remember, just because you have two vectors, it doesn't mean you're going to span 3 dimensions. Okay? To find the rank, essentially, you will combine the vectors as columns of a matrix, find the REF, and the number of leading pivot variables is then the rank. Okay? That's how you find the rank. And that's how you can find a minimum dimension spanned by your vectors. Okay, so I previously mentioned that you can have two vectors and they will span the same space, right? There are two different ones, and both of them are capable of hitting the point D, right? But if you were to look at them carefully, which which basis would you rather use to reach D? Well, for most people, the second basis makes a lot of sense. The size is 1, therefore, and this size is 1, and they are perpendicular to each other. Therefore, over here, the bases, we can almost read it, right? So this is 5 of these, and then 5 of these, and then what is this? 4 of these. So are these are called orthogonal or orthonormal bases. And having these bases would be really, really nice. In order for us to achieve these kind of bases, in general, we like to move, like if we have one like this, for example, that size of 3, we want to scale it back and make this into 1, just the size of 1. And that this act of converting a vector that's larger than 1 back to 1 is called normalization. Normalization. Okay. And these vectors that are size of 1 are called unit vectors. So unit vectors. So you want to use unit vectors because they're the preferred set of bases. Right? We often represent data, right, using independent bases. So we can represent it like this. But now remember I told you we would prefer to do this. So very often the first step we do is we scale it back. So for a vector, we make it the size of 1. And like I told you, the act of scaling this back to the size 1 is called normalization. Now, as a convention, in fact, as a convention, when you talk about bases, like people almost always scale it to 1. So how do you scale a vector to 1, right? Well, first, what does that even mean? Well, a, a vector size of 1, it means the length is 1. And we learn how to calculate length. And we're going to use the most common one, which is the L2. L2, right? Which is just the distance, right? So when the length, when the vector is unit vector, therefore the length is 1, that implies that if you calculate the length, then the length is going to equal to 1. So if you calculate length, so this square times this square root, that give us 1. Again, similarly here, that give us 1. That's what that means. It means to be a unit vector. Okay, and this is an example of not a unit vector. 2, 1, 2, 1. So this is not a unit vector because 2 square plus 1 square is equal to square root of 5. So obviously not 1. So if your boss, if you end up working at Google, asks you for the ideal basis, don't be a noob. Always give them the unit vector. Okay, ideally, they should also be perpendicular. Okay, so equation for the unit vector. So how do you scale this vector back? Well, the way you can do it is divide the vector. So this is the vector by the length. So you calculate the length, right? So for example, this is the vector 2, 1 right here. So you calculate the length, which is right here, square root of 5. Right? You calculate square root of 5 and you divide the entire vector by square root of 5. So it's 2 divided by square root of 5 and 1 divided by square root of 5. You can double check your result. So the final result is this. Now, if you calculate the length, notice that it's now going to be just length of 1. So that's how you essentially scale a vector. You calculate the length and then divide the vector by the length. And then the result would essentially have a length of 1. So now the way to calculate the length is also known as L2. So basically you just take the vector and divide by L2. Okay, so now you want to pause the video again, give this a try. Practice turning these vectors into unit vectors. Pause the video. I'm going to move on. So you will see essentially I just calculate the L2 norm and then I divide each vector by the L2 norm. So not hard. Like that's how you essentially scale it to the size of 1. Now, the first thing is, remember, we scale them. The first part is we scale them back to 1. The second part is ideally we want them to be perpendicular. So that's the second part. Now, in linear algebra, the concept of perpendicular for the bases are called orthonormal bases. So these are orthonormal bases. And orthogonality is the property of having the orthonormal basis. So this is the final concept of the day. If we have two vectors, they're called orthogonal if their dot product is equal to 0. Okay? So if you have two of them, you're going to notice how they're orthogonal. If you dot these two vectors together, they're always going to be 0. So that is actually like always true. So let's see. So this one's 1, 2, and this other one is 6, 3. 6 minus 3. So let's try dotting them together, right? So 1 times 6 plus 2 times minus 3 equals 0. So correct, right? So you're used to thinking of perpendicular as this way. but it doesn't have to be along the axes. You could be perpendicular this way. You can be perpendicular this way, essentially any way. So as long as two vectors are orthogonal to each other or perpendicular. Now, perpendicular is just kind of like in 2D. In higher dimension, you want to use the word orthogonality. So here's another one. Now, orthogonal means that when you dot them together, they're going to be a zero, right? Now, orthonormal requires normalization. So if you take two vectors that are normalized, it means, if let me remind you, normalized means they're unit vectors. It also means their length is 1. Okay, so if you take two vectors of length 1 and dot them together, it equals to 0. That's when these vectors are orthonormal. Okay, so that's the difference between orthogonal and orthonormal. In general, we really, really prefer orthonormal bases because it makes life a lot easier. You have a bunch of interesting properties. So let's say we have these two vectors and they're orthonormal. Okay. One of the interesting property is that if you do x transpose times x, so remember the column vectors here are from the bases. Now, if you were to take the transpose, because they're orthogonal, right? So remember, this is vector 1. This is vector 1. This means that when you dot them together, by definition, because they're orthonormal, their length is 1. So it's going to be 1. And then when you dot the second one, right? So this vector and this vector, when you dot them together, because they're orthonormal, by definition, they are 0. Because the dot product has to be 0. And again, if you take this one and this one, if you dot them together, once again, it will be 0. And the very last one, when you dot them together, you're going to get 1. So the ones came from the fact that it's just dotting itself. When it dots itself, it's essentially giving you the length. Okay, maybe, yeah. It's essentially giving you the length. And then when it's dotting the other one, because of orthogonality, it's always going to give you 0. Now, this right here leads us to a very interesting property. Like, this is a lot of reason why we want to work with orthonormal bases. One is which, notice, x times x inverse is equal to identity. And notice, when they're orthonormal bases, then you also reach identity. That is the interesting part. That is the interesting part. You can actually use the transpose, and transpose is much easier to deal with than the inverse, right? So you can just take the transpose of orthonormal bases and then multiply, and you automatically have the inverse. So besides this, I mean, it has a lot of other nice properties, but this is one that you should understand. So yeah, this is what I was just talking about. This, when you multiply it by the inverse, it gives you identity. Yet over here, you don't need to multiply by the inverse. You just need to multiply by the transpose. And the transpose is much, much easier. So here's some Python code. Basically, this is how you can get the rank of a matrix. Okay? So the idea of the orthogonality, like if you do the dot product between two vectors, they should be 0, right? Also, you can find the norm. Yeah, you can find the norm of like y. Y is right here. So you can essentially find the length of a vector. And then if you divide by the length, it gives you a normalized unit vector. As you can see, now I find the length, it's 1. So let me go over this again. Remember, you can find a length using this. And then if you were to divide a vector by the length, essentially you will normalize it, making it a length of 1. So this one, y hat, has a length of 1. And lo and behold, if you find the norm of y hat, it's going to give you length of 1. Okay, I think this is it. This is the so for the last work, in class work, you want to identify the rank. Okay, you want to identify the null space, identify if the columns are linearly independent, if the columns are orthogonal or orthonormal, and then you also want to use Python to check. Okay, so remember, the rank is the number of leading / pivot variables. Okay, and null space, I think we've gone through that a couple of times. Now, also linearly independent and dependence. Remember, that was related to having trivial or non-trivial solution for the null space. Now, and then you can check whether the columns are either orthonormal or orthogonal. Okay, and you can lastly use Python. So yeah, good luck with this. I will see you in the next class.